All right, so if you're seeing my screen, you see the problem here. Find two positive numbers whose product is 100 and whose sum is as small as possible. So there's always two things that are given. There's kind of like this constraint equation, which in this case is the two numbers that are 100, and the second is the thing that you're trying to optimize. So what you're trying to optimize the sum this time. So you can give it a function if you want, s equals x plus y. And almost always you substitute your constraint equation into the optimization equation. But that means you got to solve for a variable, usually y, sometimes x, but usually y. So in this case, y equals 100 over x. So your s is now x plus 100 over x. Okay, and then you take a derivative. Oops, oh, that was weird. Okay, going the wrong direction. There we go. So you got to take a derivative of this. S prime is 1, and then derivative of this, hopefully by now you're comfortable, it's minus 100 over x squared. So then you set this equal to 0 and you solve for x. So you have y equals 100 over x squared.
So why is it x squared? 100 over x squared? Why is it x squared?
Okay, so this is where if you need to, you rewrite as 100 x to the minus 1.
Oh,
You're just
right,
using
right,
power
okay.
rule. Yeah.
Right.
The faster you can do this, I mean, you're gonna like that. That's I know there's a lot on your plate, but that is really important to be able to do like long term for this class, calc 2,
Yeah.
etc. So x squared equals 100. So x equals plus or minus 10, but it said two positive numbers. So we want to use x equals 10. But we need the other number because it only gives you, we're looking for the two numbers. Well, we need to find y. So if x is 10 and x times y equals 100, 10 times y equals 100, y equals 10. So there's your answer.
Okay.
What would you like us to look at next?
Let's do the second one. Let's do number 2.
Sometimes you have to draw a picture. This one, definitely a picture would help kind of organize the problem. Okay, so there's a rectangle. It's got a perimeter. That's 100. And I like to use x and y, like to keep them consistent. X is horizontal, y is vertical. So there's always a constraint equation. So the constraint is that x plus y plus x plus y, because that's the other part of the fence, equals 100.
Right.
So 2x plus 2y equals 100. Okay, that's your constraint equation. Now we're trying to maximize the area. The area is x times y. So then you need to solve this one for y and substitute it in. All right, so do you recall how to do that? You're going to solve this one for y here, this equation in the middle.
Yep,
okay,
yep.
So y ends up being 100 minus 2x over 2. Might be good to simplify that to 50 minus x, and that's what's going to go in here. So area equals x times 50 minus x.
And then solve for x.
Well, this is the thing you got to take the derivative of, but before you do that, I would distribute in. So it's 50x minus x squared. And then now you can take a derivative.
Okay.
So that's 50 minus 2x. You set that equal to 0. And then you solve for x. X equals 25. All right, so they want the dimensions. If we go back to our original picture, this is x and this is y. We now know that x is 25. So how do we find y? Well, we've got that equation, 2x plus 2y equals 100. So 2 times 25 plus 2y equals 100. You end up getting 2y equals 50 and y equals 25. All right, so any questions on that? That's how you find the dimensions of the rectangle.
All right. No questions on that.
Great. So you sent a lot of other optimization problems also.
So those are optimization. Those are just
Are they? They're
problems.
just related,
Those are
right?
problems over test.
Okay.
Over all the tests, yeah.
Yeah, eight's kind of an optimization problem.
Yeah.
And I guess this other one is to find the maximum vertical distance. But yeah.
Oh, it is?
Yeah, I mean, I would classify it as that.
Oh, it says use the closed interval method.
Okay.
I didn't remember what that was during the test.
So we can go to 3. 3 is a the river problem.
Yeah, I want to do all of them.
Okay.
So
We
really
get, okay, we'll do them all. All right, I'll just keep going. Yeah, these are definitely the longest. They're the most difficult. But as I said, you
Oh, wait, I want to wait. Never mind. Just kidding.
You sure you want me to keep going on this one? Okay.
Yeah, that's fine.
All right. The pasture must contain 180,000 square meters. Okay, so there's a pasture here, x, y, and the constraint equation this time is x, y equals 180,000. Okay, so but that's not what you're trying to maximize. This time you're trying to minimize. You're trying to minimize the amount of fencing. The fencing is x plus 2y because there's another y over here, but there's no fencing along the river like that. So again, you always solve and then substitute. So we're going to solve for y. Y is 180,000 over x. And we'll substitute that in here. F equals x plus 2 times 180,000 over x. All right, and then you got to be able to take a derivative of this. So let's maybe just clean this up just a tiny bit here. X plus 360,000 over x. So your derivative f prime is 1 minus 360,000 over x squared. Set that equal to 0 and solve for x. So again, this is kind of like that first problem we did. You get 1 equals 360,000 over x squared. X squared equals 360,000. So x equals 600 when you do that.
Okay.
All right, so that's x. Oh, geez, I did it again. Okay, so that's x. Okay, and we need y because we actually need to find the fencing for it. So to find y, we got to go back and use our constraint equation. So y is 180,000 over x. So it's 180,000 over 600, which ends up being like 300.
All right.
So the total amount of fencing, which is what it's asking for, is the x plus 2y. 600 plus 2 times 300 is 1200.
Okay. All right, let's start doing those singular problems.
Okay. Do you want me to start with a certain one here?
No, it doesn't really matter.
Okay. I want to switch to something different, like that way cover as much as we can.
Okay.
All right. So I'm going to cover 5 here. 5 here. So find the critical numbers of this on this interval. So you gotta take the derivative. You gotta be able to find f prime of theta 4 minus secant squared theta. And then you got to set it equal to 0. So you got to set 4 equal to secant squared theta. It helps here to actually write secant squared as 1 over cosine squared theta. And then you can kind of manipulate this equation a little bit. It's 4 cosine squared theta equals 1 because you're diagonally multiplying. And then cosine squared theta equals 1/4. You take a square root of both sides. So cosine theta equals plus or minus 1/2. So you got to figure out where on the unit circle, but in this window that they're giving you from minus pi over 2 to pi over 2. So let me get that in here. So they're asking from here to here, cosine equals plus or minus 1/2. So cosine is the x value on the unit circle. So it's here, and then it's here. And that's pi over 3, and then minus pi over 3.
Okay.
So as a reminder here, you definitely got to know your unit circle, one last time. All right, so I'm going to move to 6. This is the car driving problem that creates a triangle. It's a related rate. All right, 2 grandmothers driving cars start moving from the same intersection. One travels south at 10 miles per hour, and the other travels east. So one is going south, one is going east. Okay. They tell you how long they've been driving because that's critical. You got to figure out like how far apart are they? So 90 minutes is 1.5 hours. You want to convert that to miles per hour. I'm sorry, you want to convert minutes to hours because you're going to multiply by miles per hour. Because in 10, the distance going this way, x, is 10 times 1.5. So that's 15. The y, I'm sorry, this is not x, this is y. I'm sorry, this is y, this is y, not x, because it's going down. Okay, and then the other direction, x is 16 times 1.5, and that's 24. And so you can figure out how far apart they are, which is probably reasonable to figure out. That's 15 squared plus 24 squared square rooted. Which I don't know what that is. I don't know if that even works out nicely. It does. So this is a 5, 12, 13 triangle with the multiple of 2. So no, it's not. It is not. So the other one that sometimes comes up is 3, 4, 5. I guess, I don't know. We'll just get that number, but whatever that is, we'll get it. Okay. Now it's asking for the rate that the distance between the two is changing. So you know to set this up as x squared plus y squared equals d squared. So now you take a derivative. Your derivative is 2x, x prime, plus 2y y prime equals 2d d prime. And you're interested in d prime. So your d prime, all the 2's cancel, is x prime plus y prime over d. So we just have to take all these numbers we just found. So the x value is 24. X prime is 16. That's how fast it's traveling. Y is 15. I'm choosing down to be negative, although I don't know that that's quite right in this problem. Probably should just go with positive on the y prime because the distance between them is getting further apart. So we'll keep y prime positive at 10. And d is that thing we didn't find, the square root of 15 squared plus 24 squared. Is there anything on that one you would like to discuss more about, or?
No.
Okay.
Yeah, we could do a different one. Move on, or yeah, move on to different.
Okay, so go to 4. After this, you probably want to tell me what you want to do next. Here we go. So this one, the way it reads maybe is confusing. You want to only use sine and cosine. So this cosecant is really 1 over sine x. And they're giving you the answer, but they're saying like, use the quotient rule for this, not the like you can't just say, oh yeah, it equals that. You have to actually use the quotient rule on this thing in here. So quotient rule says derivative is bottom times root of the top minus top times root of the bottom over the bottom squared. Okay, so it's d dx of sine 1 over sine x becomes bottom sine x. The derivative of 1 is 0 minus 1 times the derivative of sine x. The derivative of sine x is cosine x all over sine squared x. So this first term is 0 because anything times 0 is 0. And so you have this minus cosine x over sine squared x. And it's supposed to equal, this is the hard part. It's supposed to equal this up here. It's minus cosecant x cotangent x. So a non-obvious thing to do here is to write minus 1 times cosine x, but on the bottom to write sine x times sine x. Again, this is not obvious, so until you've seen it, you wouldn't necessarily know to do this. This one on the right, this is your cotangent x, and this one on the left here is your cosecant x.
Okay. Yeah, he put this on the test. I don't even think he showed us that before.
Yeah, so you could reasonably do it for really anything. This could be cotangent, secant x, tangent x. It's all somewhat reasonable. All right. I mean, I skipped some. Do you want me to go through those? Is there other stuff you want us to go to? What?
Did we do the number 9 one? The sum of the first number and 4 times the second number is 100.
Yes, we can do that. We did one kind of like this to start out,
Right.
but this one has a little different relationship between the two. Okay, so again, there's the constraint. The constraint here is that the first number x and 4 times the second number y is 1,000. That's your constraint.
Right.
And we want to maximize the product. The product is x times y. It's x times y because the first number is x and the second number is y, not 4 times y. So on rare occasions, you almost always solve for y. And this time I'm going to solve for x. X equals 1,000 minus 4y. If you solve for y, you end up having to deal with some fractions, a few other things. This will ultimately end up being easier. So now when you substitute this in, you get P equals 1,000 minus 4y times y. And again, kind of like those earlier problems, you definitely want to distribute this in. So it's 1,000y minus 4y squared. Now you're ready to take a derivative. So the derivative is 1,000 minus 8y. You set that equal to 0. And you get y equals 125.
All right.
Okay, but that's only one of the numbers. You got to find the other numbers. The other number you find by doing this. 4 times 125, that's 500. So x is going to be 500. All right, is that okay?
Yep.
Great.
And then the last one is the number 8, the closed interval one, right?
We can do that one, sure. Yeah. I don't really know. Oh, okay. The closed interval method means you have to test the endpoints. I see. Okay. Yeah, all right, we can do this for sure. All right, so the vertical distance between the graph x plus 2 and the parabola y equals x squared on the interval minus 1 to 2. Okay, so let's see here. The vertical distance is the difference in the y values. So the difference, okay, this maybe is more complicated than it seems. The distance is y2 minus y1. And this is like y2 and this is like y1.
Right.
So it's just x squared minus parentheses x plus 2 equals 0. I'm sorry, equals d. And we can distribute this. So it's x squared minus x minus 2. And that's the thing you're trying to minimize. So that's the thing you're going to take the derivative of. D prime 2x minus 1 equals 0. X equals 1/2.
Okay.
All right, so now the reason you're using the closed interval approach is because you have to test the original function, this one up here, actually we use this line right here. And we test the endpoints and then the critical points. So we want to find d of minus 1, d of 1/2, and d of 2. And whichever one is the biggest, or let's go look, yeah, the biggest is the winner.
Okay.
So it's minus 1 squared minus a minus 1 minus 2. So that's ends up being 0. So 1/2 squared minus 1/2 minus 2. So that's like 1/4 minus a half, so it's minus a fourth. So this ends up being minus 9/4. And then, so that suggests I may have gotten the order wrong because the distance is negative.
Uh-huh.
2 squared minus 2 minus 2 is also 0.
So yeah, how do you know what order to?
Well, this is the right answer. I had the distance wrong. That's why the instructor said to draw a picture. You know, here's x squared, here's x plus 2. So I guess I should have had like that x plus 2 first.
Oh, okay. All right. I want to do a problem like, let's see what they're called. It's the one where you find it's the problems where you find the area under the graph of function using the left or right sample points.
I can make one up, or you can find one if you want.
Yeah, because I don't have any like on me right now, but I can look at it.
Okay, so let's say f of x equals x squared. And we want to go from 0 to 4. And we want n equals 4. So to do this, you first have to find delta x. Delta x is b minus a over n. This is a, this is b. And so that's 4 minus 0 over 4, which is 1. All right. So now your left sum is delta x, but you start at the left side. And you look at this window here from 0 to 4, and you want to find f of 0. That's your leftmost endpoint. But then you want to find 0 plus delta x. Like you want to move over 1 unit. So this becomes f of 1 because delta x is 1. Then you want to do this again, so you want to find f of 2 because you keep going on this. And then you want to find f of 3. You stop when you have the 4 points that you need. So your delta x is 1 for this problem here. So your left sum, you have to get these values. You have to put 0 into x squared.
All right.
So that's 0 squared plus 1 squared plus 2 squared plus 3 squared. Is that okay?
Yep.
All right. So now your right sum, which is very similar, but it skips the first value. So it's, you got to go over 1 point. So it becomes f of 1 plus f of 2 plus f of 3 plus f of 4.
Okay.
So that's 1 squared plus 2 squared plus 3 squared plus 4 squared. You get that value.
All right.
And that's a trivial example, but it runs through all the things. You have to be given some sort of function. You have to be given a window, an a to b, and you have to be given an n. Then you need to know whether you're doing a left or a right sum.
Okay. That's all I really had today, honestly. I was just gonna do a little short meeting and then just study. myself.
All right. Well, I greatly appreciate you scheduling. Good,
Yeah.
best of luck on your exam. You seem to be doing your best here to try to get through this thing. So you're almost to the finish line. Just keep working hard. You'll be there.
All right. Thank you.
You're welcome. Have a great night. Bye now.
You too.